Now, we want to say that, well, if H happens to be the total distance from here up to the opening, okay? Then additional heating will continue to heat the gas here, right? But you're not going to be getting any more pressure. So the additional heating will occur with no additional pressure change. That being the case, this no longer holds, does it? So what's got to give? PV equals nRT. You continue to heat it. Continue to change T. What's now staying constant? And the number of moles, right? Very good. Well, P and N stay constant, so that now the volume is proportional to temperature. So that volume over temperature is constant. So if we're heating temperature T2, and let's just call that T max because that's as hot as we're going to let it get. V max over T max equals and I really can't call that V max. Okay, and I'm just getting messed up with subscripts. I got to call this not V max but V2. Okay, but V2 over T max is going to equal V1 over T1, so V2 equals V1 times T max over T1. Makes sense? Okay. Well, now we can graph what's going on here on a graph of pressure versus volume. We start at V naught P naught. Yeah, in other words, we have some pressure and temperature at this state. Okay? And then we go to what? When we're here, what's the pressure and what's the temperature? I'm sorry, what's the pressure and what's the volume?
So it's all constant, right?
Well, pressure increased, but volume's a constant there.
Well, what we have is we have constant volume, so this is going to be a vertical line. Kind of missed it, you get the idea, right? So now we have P1, V1, and we did it along a straight line on a pressure versus volume curve graph, okay? Now what's the next part gonna look like?
Pressure's gonna stay the same, but volume's gonna change.
Pressure's gonna stay the same, volume's gonna change, right? So here we have P1 V2. Okay? Now, another thing, and I'm not gonna explain this right now, and if it comes up in a test, I'll give you some explanation, because we haven't talked about it. But I can do that, because there's a very simple model for this that will convince you of it. The work that you've done, the work that the gas has done, is equal to the area under this section of the graph. Okay? Gas has done work equal to the area, the indicated area. Okay? At the expense of internal kinetic energy. Internal kinetic energy means the kinetic energy of the molecules in the gas. Molecules are doing work. They're basically hitting the surface of this water and driving it down a little bit lower to drive the water up through the tube. And they're losing kinetic energy, because if a particle hits a receding surface and bounces off, it loses kinetic energy. Of course, you're also adding energy to heat the gas, right? Okay? So it's at expense of kinetic energy, internal kinetic energy, but you're increasing the temperature, so you're adding more energy than you're spending to do this work. Got that? Make sense? If you understand energy conservation and so forth, it should make some sense. Okay? Now, I expect you'll be able to do these calculations. Okay? That's fairly simple, so make sure you understand this. If I ask you to do any more, like with the energies and stuff, I'll prompt you. You know, I'll prompt you and I'll tell you, okay, well, can't phrase it right now. Everything I'd say would be really pretty simple. Okay? Now, just quickly, the area under this thing is going to have units of what? It's units of pressure times units of volume, right?
Yeah.
In SI units, that's newtons per square meter times meter cubed, which is what?
Joules.
Yeah. Very good. So it's at least plausible that this is work. Okay? There's a very easy example, but we don't have Let me just show you. But I'll give you a complete explanation if you need to use it, okay? If you need to convince it for some reason. We got a piston. You got gas, right? How much force is the pressure? P. The area of the piston, which is equal to the cross-sectional area of the cylinder, is A, right? Okay? So if the piston moves a small distance, how do you figure out how much work is done on the piston by the gas? Piston moves a distance we'll call delta Y. Small distance, okay? Well, the pressure, the force on the piston is A times P, cross-sectional area times the pressure. It's choppy, a little sloppy. And I add to that. Okay, so you have this, right? So the work is AP delta Y. Well, the change in volume is A delta Y. So the work is A delta Y times P, which is P times delta V. Right? And that's exactly what the dimensions of this rectangle are. Okay? So we're talking about the work you can do by heating a gas. Now, in most courses, we'd spend a little more time on this, but since the course you'll be expected to have has more electromagnetism and probably doesn't even cover much of this, not much thermodynamics, we haven't done that, okay? But this gets you right up to beginning to understand a little bit of thermodynamics and the efficiency you could get out of a system like this. You can calculate the work. Now to run a cycle of this thing, you then have to return to the original state, which means you've got to get from here to here somehow, okay? Well, you could just suddenly let off the pressure, which would give you a pressure volume curve that looks something like this. It'd be concave up. And then you can cool it back. And in doing so, the net work you get would be the area enclosed by the curve. Okay? So there might be something related to that idea on the test, but only with a fair amount of explanation. If you do these calculations and understand that little bit about pressure volume graphs, I'll explain the rest. I'll give you enough information. Okay?